Hello students, this video is for Unit 1, Lesson 5, the lesson on distance between points. In this lesson, I'm going to be showing you how to find the distance between 2 points, in other words, the length of a line segment, using a formula and also using a theorem that you're very familiar with from other classes. In the notes, it tells us the learning target, which states, I can find the length of a line segment using the distance formula and the Pythagorean theorem. That Pythagorean theorem is something that you should remember quite well from 8th grade and then 6th grade, all the other different smaller grades that you learned about Pythagorean theorem, which deals with right triangles. Two specific things that you should remember about the Pythagorean theorem is that it helps you find the missing side of a right triangle, and that it takes the form a squared plus b squared equals c squared, where a and b are the legs or sides of the triangle, and c is the hypotenuse of the triangle, the longest side. Now that we're on the same page on that, the do now question asks us to find the length of each missing side given the other two sides of the triangles. Take a few minutes, pause the video, and try to answer these questions, and then come back to see if you get them right. You can see that in this first problem, we labeled A, B, and C. Generally, students choose A as the smallest leg, B as the second smallest leg, and then C as the longest side, the hypotenuse. The A and B are interchangeable, but if you always do A is the small side and B is the medium side, you will be good to go. So a squared plus b squared equals c squared, substituting those values in and evaluating, 9 being 3 squared and 16 being 4 squared. We're adding those together and then solving for x, getting x is equal to 5. So this is a 3, 4, 5 right triangle. Again, take a look at questions 2 and 3, see if you can get them right. And here you can see that question 2 ran the same as question 1. The y was the hypotenuse, so that's the missing number that we're trying to solve for, and both of the legs were given to us. Number 3, notice that the hypotenuse is given to us, so the Pythagorean theorem will be filled out a little bit differently. In this third example, we had 2 knowns and 1 unknown, similarly to the previous problems, but in this case, one of the unknowns was one of the legs. So we had to substitute in for A and C rather than A and B, but most of the other algebraic manipulations were very similar. We went from the square root of 544 to 4 radical 34. This is a simplifying radicals question. We went over this in a previous lesson. If you're not sure how to get from square root of 544 to 4 radical 34, go back and watch that video on simplifying radicals. Now let's move on to the purpose of the video here, which is the distance formula. It is a formula that you learn about in algebra. It's a formula that helps us find the distance between 2 points, or in other words, the length of a line segment, by substituting values into an equation. And this D represents the distance or the length of the line segment. It is the quantity, the amount of distance between the 2 endpoints. The formula might look like it's very complicated, but in reality it's very simple. All it does is take 2 points, an x1, y1, and an x2, y2, and say, let's take those numbers, substitute them into the formula, and evaluate. Anytime you're dealing with a line segment, it'll have 2 endpoints, and both of those endpoints would be identified by an x and y coordinate point. All we need to do is substitute those values into the distance formula in order to find the exact distance between the 2 points. In the example that I'm going to give, these are the 2 coordinate points, r, which is -3, 2, and t, which is 4, positive 1. Once I graph these 2 points, I can see that the distance in between them is going to be this line segment here. And in order to find that length, I can use this distance formula, which I just showed you, and I'm going to walk you through the implementation. The first thing we're going to do is write out the exact distance formula, write out the formula first before substituting. Then we'll identify one of these 2 points to be the first endpoint and one to be the second endpoint. It really does not matter, regardless of which way we substitute them into this formula, we're still going to get the same value. I'm going to choose that r is the first and t is the second only because that's the order from left to right. But again, it would not matter which way we plug them into or substitute them into this formula. And now that I've identified them as x1, y1, and x2, y2, I can easily say, well, x2 is supposed to be 4, y2 is supposed to be 1, etc. So I'll show you that substitution now. And once we complete that substitution, we can move on to simplifying. Again, we're using PEMDAS, so parentheses comes first. The 4 minus -3 and the 1 minus 2 are going to be evaluated first. Now at this point, after parentheses is done, we're going to move on to exponents, and there are 2 exponents to evaluate, the 7 squared and the -1 squared. And one common mistake that students make is they turn -1 squared into -1. Remember that -1 squared is -1 times -1, which would give you a positive 1. Any integer squared is a positive number. So now I just do 49 plus 1 inside the parentheses, and I've got my radical. And of course, you know that most of the time this number inside the square root is not a perfect square number. You can simplify it by using the simplifying radicals technique. Take a moment to see if you can remember how to do that. All right, hopefully you were able to get 5 radical 2. Now, remember the question is, what is the length of RT? And the answer is that RT is 5 radical 2 units. I know that doesn't sound like a number to you, but 5 radical 2 is an exact simplified radical answer, so it's totally fine for me. So we'll label this answer as the length of RT is 5 radical 2. Now, one nice thing that we can do with problems with a graph involved is we can check our answer by using a second method. Again, I'm going to graph these 2 points to try to use the distance formula, but then I'm going to try to use the Pythagorean theorem to do the same thing. So first, here's the Pythagorean theorem. So here's our line segment, and it does ask whether we can use the Pythagorean theorem to find the distance between these 2 points. It turns out the answer is yes. Even though this looks like simply a straight line, since it's graphed on a coordinate grid, I can easily connect the dots in order to make myself a right triangle and then find the hypotenuse of that right triangle. And once I connect those 2 pieces to form that right triangle, I can identify how long or how many units the leg here is and how many units the leg here is in order to figure out what to plug into or substitute into my Pythagorean theorem. So I'm able to count 7 units up and down and 2 units horizontally. So let's substitute that into the Pythagorean theorem to try to find this, which I'm going to call the hypotenuse, or C. And this substitution should have went fairly smoothly. 2 squared is 4, 7 squared is 49. Add them together and then square root both sides to get the x by itself. The square root of 53 isn't something that could be simplified using the simplifying radicals technique. So we just say that the distance of AB, or the length of line segment AB, is 53. So that's what we got with the Pythagorean theorem. Should the distance formula give us the same thing? Well, let's check. Remember, the distance formula requires us to write out the formula first, and then we will annotate to try to figure out which one is x1, which one is x2, etc. So I'm saying that point A is going to be the first endpoint, and point B is going to be the second endpoint. So this is x1, y1, x2, y2. And once I've labeled my problem, I can move on to substituting the numbers into the formula. Just like in the previous problem we did the distance formula in, we have the parentheses as that next step. We're going to try to evaluate everything inside the parentheses, then do the exponents, and so on. 4 and 49 add up to 53, and the square root of 53 can't be simplified, so we're left with AB is equal to 53. Now keep in mind, that is the same exact answer that we got previously, which should lead you to believe that we can either use the distance formula or the Pythagorean theorem in problems like this. If you're looking at a problem that can easily be graphed, the Pythagorean theorem is sometimes a little bit more straightforward, maybe a little easier to substitute in. It doesn't require so many substitutions. However, when you're not given a graph, like in this example, we weren't given a graph, it's a little bit easier to use the distance formula because all you need to do is be able to add, subtract, multiply, and divide. You don't need to graph at all. And it prevents you from making graphing errors just by using the distance formula. And the last step of this video is for you to do some independent practice. What is the length of a line segment whose endpoints have coordinates 5, 3, and 1, 6? Go ahead and try that problem out. Pause the video for a moment and then come back to see if you got it right. All right, here you should be able to make out the substitution that we did. We labeled the 2 coordinates as x1, y1, x2, y2. Substitute, evaluate, continue evaluating, and then simplify the radical as much as we can. In this case, it is a perfect square number, which can be simplified to simply 5. So we found out the length of the line segment is 5 units. If we were to use the x and y coordinates to do the same thing, we counted these boxes to be 3, these boxes to be 4, and that means the legs are 3 and 4 respectively. The hypotenuse is the missing element. So we substitute it into the Pythagorean theorem and solve for C is equal to 5. A couple of interesting things to note before we end this video. You should recognize that this 3 and this 4 are the distances between the 2 points, the vertical and horizontal distances. They also show up here. They are part of the distance formula. So when you think of the distance formula, you can think of it being an algebraic representation of the Pythagorean theorem. In other words, this is the Pythagorean theorem without the graph. Interesting. All right, hopefully this was helpful to you. Remember that this was the lesson for the Unit 1 Lesson 5 lesson called Distance Between Points. Good luck studying.